Pluto, a faraway and perplexing, more modest planet, was once a singular member of our solar system's planetary family. However, later disturbing statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a dazzling revelation. They proposed that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a rare cosmic phenomenon, or is there something else to this looming celestial collision? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet partly due to its curious orbit, remains a subject of fascination and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potentially dangerous collision between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's path is marked by its highly eccentric shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, measured at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all interact in a complicated way. Terms like asymptotic libration, scope libration, and VSK oscillation are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a type of libration. Regarding Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of safety from potential impacts. Another critical factor is the VSK oscillation. This phenomenon, named after researchers Vyacheslav V. Kalygin, Sergei P. Sannikov, and Kirill A. Yurov, explains how three celestial objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pulling affects how they move. In Pluto's case, VSK oscillation helps us understand why its orbit around the Sun is so unusual. Despite apparent chaos, this oscillation helps maintain Pluto's orbital stability over incredibly long time scales. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is actually chaotic, with minor deviations in initial conditions leading to significant differences over thousands of years. However, these peculiar properties of Pluto's orbit have been found to maintain stability over unimaginably long timescales, effectively controlling the chaos. Recent computer simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where, for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in protecting Pluto's orbit, and Saturn contributes as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for a very long period, possibly even billions of years. It seems Neptune, Jupiter, and Saturn work together to ensure Pluto can continue moving safely through space without running into trouble. These peculiarities are crucial in the broader context of the universe for maintaining the order and consistency of celestial bodies' movements. Without these mechanisms, the solar system, as we know it, would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is essential. This provides us with a clearer picture of the solar system's dynamic nature. Pluto's situation illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces. Orbital mechanics additionally show the significance of consistent perception and investigation of these peculiarities to better understand our place in the universe. Examining the depths of space often leads us to confront the whimsical nature of celestial bodies. Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been incredibly helpful for researchers to understand how Pluto moves in space. These simulations use complex mathematics to mimic how Pluto, along with other space objects like Neptune, pull on one another. By changing small details in these simulations, astronomers can see how even tiny changes can have a big impact on where Pluto ends up. In the late 1980s, these simulations revealed something truly fascinating about Pluto's orbit. Despite having mechanisms like asymptotic and latitude libration to keep it stable, its orbit can still be wild and unpredictable. If you start with even a small difference in where Pluto is or how fast it's moving, over many years, its path can end up looking drastically different. However, despite this chaos, Pluto's orbit remains stable for a very long time, billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it may seem chaotic at first. Predicting major events, especially when they involve chaotic orbits like Pluto's, presents enormous challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a strong foundation for understanding and predicting the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to drastically different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made tremendous strides in understanding space, the case of Pluto reminds us how our knowledge of the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates that the presence and position of each planet can have a cumulative effect, influencing the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces working to prevent such an event, deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the uncharted expanses of space. Tyson's position on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but rather as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees not only the complexities of Pluto's orbit, but also its interactions with Neptune from a perspective that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This makes studying its trajectory particularly important for understanding the broader forces at play in our solar system. As he often notes, science is always evolving, and Pluto is a perfect example of how new knowledge can reshape our view of the universe. Tyson's concerns regarding Pluto's long-term stability stem from the ever-changing dynamics of our solar system. Despite its current stability, Tyson acknowledges that future shifts in the gravitational interactions between Pluto, Neptune, and the Sun could lead to unexpected changes. The delicate balance that currently keeps Pluto's orbit stable may eventually be disrupted by changes in the Sun's gravitational influence, the movement of other planets, or even the impact of new forces yet to be discovered. Tyson's emphasis on these future uncertainties serves as a reminder that the universe is a constantly shifting system, and that even what seems stable today could change in unforeseen ways. His warning about the possibility of a collision between Pluto and Neptune highlights the evolving nature of our understanding of celestial mechanics. As we continue to study Pluto and its peculiar orbit, we must consider how the forces of gravity and the complex interactions between celestial bodies will continue to shape the future of our solar system. The potential for a Pluto-Neptune collision may be a distant possibility, but it underscores the importance of ongoing research and our constant need to adapt our understanding of the universe as new discoveries are made. Ultimately, our understanding of space, time, and gravity will continue to evolve, revealing ever more astonishing and captivating phenomena. This is the journey that awaits us as we look to the stars for answers to questions that have long eluded us. Pluto's future may seem uncertain, but with every new study, we uncover more about how our solar system works. The vast dance of planets like Neptune and Pluto reminds us of the immense complexity and beauty of the universe. While it is clear that Pluto's orbit is likely to remain stable for the foreseeable future, the potential for change is always present, hidden within the chaotic nature of space. Pluto's journey through space, despite its current stability, is far from simple. As a dwarf planet, it provides a unique case study of the intricacies of celestial mechanics and the forces that govern the solar system. The fact that its orbit crosses Neptune's without leading to a catastrophic collision challenges conventional expectations. This fascinating scenario invites further exploration of how various forces work together to prevent objects in space from colliding. While Neptune's gravity is often considered a dominant factor in shaping Pluto's orbit, the interactions between all the solar system's planets, especially the gas giants, are crucial in stabilizing Pluto's path. Jupiter, with its massive size, plays a vital role in this.